Welcome to the fascinating world of crystal structures. Today, we'll explore how atoms and ions are arranged in solids. In solid-state physics, the crystal structure is like the blueprint of a material. It's fundamental in determining critical physical properties. Think of it as the DNA of a solid material. Just as your DNA defines your characteristics, a crystal structure defines a material's mechanical strength, electrical conductivity, and optical properties. By understanding crystal structures, we can predict and manipulate how materials will behave in different conditions. Let's categorize solids based on how their particles are arranged. We have four main types. First, crystalline solids, which have a regular, repeating pattern of particles over long distances. Imagine a perfectly organized Lego structure. That's a crystalline solid. Examples include metals, salts, and diamonds. They have definite geometric shapes with well-defined boundaries. Next, amorphous solids. These are the rebels of the solid world. Their atoms or molecules are completely disordered, lacking a sharp geometric structure. Think of glass, rubber, and plastics. They're like a messy room with no particular arrangement. Then we have polycrystalline solids, which are like a collection of tiny crystals with different orientations. Most metals, ceramics, and some polymers fall into this category. Each small crystal or grain has its own internal order, but when you look at the whole material, the grains are randomly oriented. Lastly, quasicrystalline solids. These are the most intriguing. They display a form of symmetry that doesn't repeat periodically. Imagine a pattern that's orderly but doesn't follow a strict, predictable rule. That's a quasicrystal, often found in unique alloys. Let's dive into the heart of crystal structures, the unit cell. Think of the unit cell as the fundamental building block of a crystal, just like a single Lego piece that you can use to build an entire structure. It's the smallest repeating unit that, when stacked together in three-dimensional space, creates the entire crystal. We have two types of unit cells, primitive and non-primitive. A primitive unit cell contains just one lattice point, while a non-primitive unit cell has multiple lattice points, like a body-centered or face-centered arrangement. To completely describe a unit cell, we use 6 parameters, 3 edge lengths, A, B, C, and 3 angles, alpha, beta, gamma, between these edges. Imagine these as the dimensions and angles that define the unique shapes of our crystal's fundamental building block. Each crystal structure will have its own unique set of these parameters, making every crystal structure special and distinct. Now, let's explore the 7 crystal systems, each defined by unique symmetry and geometry. First, the cubic or isometric system. Here, all edges are equal and all angles are 90 degrees. Think of a perfect cube like table salt, NaCl, or diamond. Next, the tetragonal system, where 2 edges are equal, but the third is different, still maintaining 90-degree angles like rutile. Then we have the orthorhombic system, where all edges are different, but again, all angles remain 90 degrees. Sodium nitrate is a great example. The hexagonal system is fascinating. 4 edges are equal, with angles at 90 and 120 degrees, like graphite. Trigonal is similar but with slightly different angles, such as quartz. The monoclinic system has 2 different edges and 190-degree angle, like gypsum. Finally, the triclinic system, the most complex, where all edges and angles are different. Turquoise is a beautiful example of this system. Each of these systems represents a unique way that atoms can arrange themselves in space. Translation vectors in a crystal lattice define the positions of lattice points relative to each other. In 3 dimensions, These vectors are represented as B and C. They specify the periodicity of the lattice, allowing any lattice point's position to be determined using the formula R equals N1 times A plus N2 times B plus N3 times C, where N1, N2, and N3 are integers. These vectors are fundamental in constructing the entire lattice by repeating the unit cell. Let's talk about lattice planes. Imagine them as invisible slicing planes that cut through a crystal structure. These are imaginary flat surfaces that pass through a set of parallel lattice points in a crystal. Think of them like cutting a loaf of bread. Each slice represents a lattice plane. The space between these planes is crucial and is called interplanar spacing, denoted by the letter D. This spacing is like the distance between each slice of bread in our crystal loaf. Lattice planes are incredibly important in understanding how different types of waves, X-rays, electrons, and neutrons, interact with crystal structures. Miller indices are the crystal world's coordinate system. They describe the orientation of lattice planes using three numbers, HKL. Imagine these as special coordinates that tell us exactly how a plane is positioned within the crystal structure. These indices are derived from the intercepts of planes with the crystal axes. It's like creating a map of the crystal's internal landscape. Scientists use Miller indices to precisely identify and describe different planes within a crystal structure. Think of Miller indices as the GPS coordinates for crystal planes. They help us pinpoint exactly where and how a particular plane is oriented in the crystal's three-dimensional space. Now we'll explore the basic building blocks of crystal structures. We have three primary simple crystal structures. First, the simple cubic, SC structure. Imagine atoms sitting precisely at the corners of a cube. It's the simplest structure but rare in nature due to low packing efficiency. Its coordination number is 6, and the atomic packing factor is just 0.52. Next, the body-centered cubic, BCC structure. Here, we have atoms at the cube corners plus one atom right in the center. This structure is found in metals like iron and chromium. It has a coordination number of 8 and an atomic packing factor of 0.68. Finally, the face-centered cubic, FCC, structure, the most efficient. Atoms are located at the corners and centers of each face of the unit cell. This structure is found in metals like aluminum, copper, and gold. It boasts a coordination number of 12 and an impressive atomic packing factor of 0.74. Interplanar spacing, denoted by D, is the distance between two adjacent parallel planes in a crystal lattice. For cubic crystals, the spacing can be calculated using the Miller indices of the planes, represented by H, K, and L, along with the lattice constants A, B, and C. For cubic crystals, the formula for interplanar spacing can be expressed as 1 divided by the square root of the sum of the squares of H divided by A, K divided by B, and L divided by C. In a cubic unit cell where V equals B equals C, this simplifies to a divided by the square root of the sum of the squares of H, K, and L. This spacing is crucial for understanding the diffraction patterns that occur when X-rays are directed at a crystal, which allows us to deduce the crystal structure. Crystal structure analysis is like being a detective, investigating the hidden world of atomic arrangements. Scientists use various techniques to understand how atoms are positioned within a crystal lattice. It's a crucial process that helps us uncover the secrets of material properties. The goal is to characterize and understand the intricate arrangement of atoms. By studying these arrangements, We can predict how materials will behave under different conditions, from their strength and conductivity to their optical properties. Imagine it as mapping the internal architecture of a material, revealing its fundamental blueprint. Bragg's law explains how X-rays are diffracted by the layers of atoms in a crystal. The diffraction occurs when the path difference between rays scattered from consecutive lattice planes causes constructive interference. This happens at specific angles, known as theta, which are related to the wavelength of the X-rays and the spacing between the planes. The law is mathematically expressed as n times lambda equals 2 times d times the sine of theta, where n is the diffraction order, lambda is the wavelength, d is the distance between planes, and theta is the angle of incidence. Bragg's law is widely used in X-ray crystallography to study the structures of crystalline materials, proteins, and even large, complex molecules. When X-rays strike a crystal, they are diffracted by the layers of atoms, leading to a diffraction pattern. By analyzing this pattern, scientists can determine the arrangement of atoms within the crystal lattice. This technique has been pivotal in understanding the molecular structures of numerous materials, advancing fields such as materials science, chemistry, and biology. The Lau method, named after the physicist Max von Laue, is used to study crystal structures through X-ray diffraction. In this method, a fixed crystal is exposed to a broad beam of X-rays, and the resulting diffraction pattern is recorded on photographic film or a detector. The Laue equations, which involve the incident and scattered wave vectors, help determine the symmetry and orientation of the crystal lattice. The Laue method offers several advantages, making it particularly valuable for single crystals regardless of their orientation. Unlike other methods, it uses a single broad spectrum of X-rays, eliminating the need to vary the wavelength during analysis. This method is extensively used to study crystal structures, determine symmetry, and identify the orientation of crystals. It is also useful for identifying crystalline materials and analyzing complex or unknown structures. Let's explore the imperfections in crystal structures, point defects. These are like tiny glitches in an otherwise perfect atomic arrangement. Imagine a perfectly organized bookshelf where a few books are misplaced or missing. That's what point defects are in crystal structures. Point defects occur at a single location in a crystal lattice and can dramatically change a material's properties. They affect everything from electrical and thermal conductivity to how materials diffuse and interact. We have 3 main types of point defects: vacancies, missing atoms; interstitials, atoms squeezed between regular lattice sites; and substitutional defects, where one atom is replaced by another. These tiny imperfections might sound small, but they're incredibly important. They're like the individual brushstrokes that can change an entire painting's appearance and meaning. Now, let's dive into the Schottky defect, a fascinating type of point defect in ionic crystals. Picture this as a carefully balanced system where atoms decide to take a vacation, leaving behind empty spaces. In a Schottky defect, an equal number of cation and anion vacancies are created to maintain charge neutrality. It's like removing the same number of positive and negative chess pieces from a chessboard, ensuring the board remains balanced. This typically occurs in ionic crystals with ions of different sizes. Take sodium chloride as an example. Here, both sodium and chloride ions can create vacancies. These defects reduce the material's density and can significantly impact its electrical and thermal properties. Think of it as creating microscopic holes in the crystal's perfect structure. Let's explore the Frankel defect, another intriguing point defect in crystal structures. Unlike Schottky defects, Frankel defects involve an ion taking an unexpected journey within the crystal. In a Frankel defect, an ion moves from its normal lattice position to an interstitial site. Imagine a person leaving their assigned seat and squeezing into a space between other seats. A great example is in silver halides like AgCl, where a silver ion might migrate from its regular position to an interstitial site. This type of defect creates both a vacancy and an interstitial defect. The displacement is usually smaller compared to Schottky defects, but it can significantly impact the crystal's ionic conductivity. It's like creating a microscopic shortcut for ions to move through the crystal structure. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.